All right, hello everyone, good morning and welcome to the September California-Nevada Drought Early Warning System Drought and Climate Outlook Webinar. Thank you for those who have joined us previously and those who may be joining us for the first time. My name is Amanda Sheffield and I am the Regional Drought Information Coordinator for NIDIS in California and Nevada. This webinar is co-hosted with the California-Nevada Application Program, a NOAA CAPRISA team. We host this bi-monthly webinar series designed to provide the region with timely information on current drought status and associated impacts, as well as a preview of developing climatic events. Before we get started, please note that this webinar is being recorded and the recording and a brief summary will be available on drought.gov and our YouTube channel later this week. We've got a great set of speakers this week covering current conditions and outlooks, as well as more detail on the current El Niño and what that may mean for the coming winter. Before we get started, just a few slides for those that don't know NIDIS. Our mission is to improve the nation's capacity to proactively manage drought and drought-related risks, providing those affected with the best available information and resources to assess the potential for drought and to better prepare for, mitigate, and respond to the effects of drought. We work to improve our understanding of how and why drought affects society, the economy, and the environment, and to improve accessibility, dissemination, and use of early warning information for drought risk management. We fulfill this mandate by building a national drought early warning system, or DEWS, through advancing regional drought early warning systems with new and existing networks of federal, tribal, state, local, and academic partners. What does this mean in the drought early warning system? A little bit more, this means we integrate the information on key indicators of drought to make it more usable, reliable, and timely. And we have a bunch of different activities under these different bubbles here on the figure under observation and monitoring, interdisciplinary research, communication and outreach, prediction and forecasting, and planning and preparedness. A webinar like this fits into communication and outreach. With that, I'll go ahead and get started on our great webinar. Just a reminder for folks, if you do have a question during a talk, please put them in the questions panel or in the questions box on the GoToWebinar panel. We'll do all questions at the end. And with that, we're going to go through our three speakers today, covering the Drought and Climate Update and Outlook, the ENSO El Niño Southern Oscillation Update, and then a presentation on El Niño intensity matters for Western U.S. precipitation. Due to some timing issues, we're going to swap the first two speakers. And so the first speaker is going to be David DeWitt, who is the director of the National Weather Service Climate Prediction Center, and he's going to give us the El Niño update. And Dave, ready to go to you.
Yeah, great. Thanks a lot, Amanda, and thanks a lot for accommodating me, and also to Dan for letting me cover more on the outlook in addition to the El Niño. And I'll say this 3 times, and feel badly I'm actually not going to be able to participate and listen to the other 2 talks. I'm particularly interested in seeing Andy's, and we'll reach out to you to get a copy. So the interesting thing is, despite the fact that we have very strong in our classification system, strong sea surface temperature anomalies already in the central and eastern tropical Pacific. When you look at the forecasts that are being produced by the dynamical models, and here in the US, we use the North American Multi-Model Ensemble. The European community has a similar set called Copernicus. The impacts for the fall and the winter right now are a very modest shift of probabilities, perhaps less than we might expect given the strength of the event. It's actually rather curious, and I should say this has been the case since this event started, even though the models were forecasting very strong sea surface temperature anomalies, which has played out so far. They have never been bringing along very large shifts of the probabilities for above normal precipitation, for instance, in the Southwest US. Next slide. So I'm going to cover the large-scale climate forcing El Niño at this time of year for what we would normally expect. And again, of course, every El Niño event is different. It has been a very impressive event in terms of its rapid onset and the magnitude and the distribution spatially of the sea surface temperature anomalies associated with it. Then I'll talk about the seasonal forecasts starting with October through December, and then finishing up with December, January, February, and then give a quick summary. Next slide. So we're already in El Nino conditions by the definition that NOAA uses, and the official forecast here at the Climate Prediction Center is that it's going to continue to have El Nino conditions through the January to March period with over 95% probability. As you get further into the spring, the probability goes down a little bit, as you would normally expect if we're going to get a transition out of El Nino, which would be the normal situation, first through neutral, and then it's a little early to speculate whether or not we would get into La Nina conditions, which does happen not infrequently following El Nino. So we're expecting the sea surface temperatures are going to peak sometime in the late fall into early winter, and right now the forecasters are forecasting a probability of 71% that it's going to exceed 1.5 degrees centigrade. It's already there right now, and that's expected to continue, and it is expected to grow a bit more. And that's, again, based on the dynamical modeling tools that we use, which includes both European tools like the Copernicus Climate Services, as well as the US and Canada-based tools in the North American Multi-Model Ensemble. Next slide. So this is what the global distribution of sea surface temperature anomalies look like for the previous 30-day average. And as you can see, it is a very robust event. It's got a very strong footprint or signal in the Eastern Pacific and along the South American coast. The overall magnitude, as I've stated, is quite large. And associated with this, we see that sea surface temperature anomalies in a large part of the globe are above normal. People are looking at this because of the fact that, as we know with El Nino, it does tend to drive global surface temperatures, both land and ocean, to be above normal. And since we were already in a warm state, this could have impacts for just how warm things get globally. Next slide. So starting with the first forecast, and this is for the October, November, December season. On the temperature side, we do see, and I'll just focus here on the Southwest, a modest probability for above normal temperature for this period in basically the whole Southwest. On the precipitation side, equal chances. And so for folks who may not be familiar with this sort of nomenclature, one of the ways to look at equal chances is that, in fact, we don't get much of a shift, or it's very difficult to determine the shift between the three different states. And so that indicates that it's a low predictability state. Low predictability is the way, for instance, that our colleagues in the Storm Prediction Center tend to characterize that. And again, for this time of year, for October, November, December, where you're already getting into the beginning of the peak water year and peak snowfall and rain in the southwestern US, this is interesting. And I will say, even the signal that we're seeing in the southeast US, which is usually stronger than the one we would get in the southwest US for precipitation, is also relatively weak, especially given the size of the sea surface temperature anomalies that we're seeing. Next slide. Yep, great, thanks. So as we move into late fall and into the winter season for temperature, we're seeing a more classical temperature impact from this particular El Nino event, with the northern third of the US favoring above normal temperature, or enhanced probability of above normal temperature. That does impact, in this case, a large part of California. But again, the probabilities are relatively modest for this. And then again, on the precipitation side, for the southwest US, at least for California, Nevada, and most of Arizona, it really is not a strong shift towards above normal precipitation or enhanced probability of above normal precipitation, which, given the size of the El Nino, is a bit surprising. Next slide. And so, back one. Yeah, great. So as we get into the heart of the winter, the December, January, February season, we see again on the temperature side an enhanced probability of above normal temperature for that northern third. That's a very typical response to El Nino. We're not seeing anything on the temperature response for the southern third, which also would be frequently a more characteristic response, although that would usually be below normal, enhanced probability of below normal. Then on precipitation for the very southern part of the country, including here in the topic of the briefing, the Southwest, there's a modest shift of probabilities, modest enhanced probability of above normal precipitation for Southern California, for central and southern Arizona, New Mexico, out through Texas. And this is the time of the year we would expect the largest impact associated with El Nino. And again, given the magnitude of the sea surface temperature anomalies in the central and eastern equatorial Pacific, the strength of this response is interesting at this time. And as I say, this is reflected in the state-of-the-art dynamical models, both from the European side, the Copernicus Climate Services, as well as those for the North American Multi-Model Ensemble, which consist of US models as well as models from Canada. Next slide. So in summary, El Nino conditions are here. It's a 95% chance that it's going to persist through the end of winter. 71% probability of Niño 3.4 SST anomalies remaining strong, i.e. above 1.5 degrees centigrade in the system we use. The impacts of El Nino for the southwestern US show a modestly enhanced probability of above normal precipitation. That really is, as you get into the heart of the winter, we're not seeing much of an enhanced probability of precipitation, which you might have expected for the fall season. And that's all I have. I understand we're not going to take questions, so I'll stay on as long as I can, and then I'll drop off. And I appreciate the fact that the organizers and Dan was willing to switch with me and let me speak first. Thank you very much.
Dave, since you might not be able to say it in the end, there's one quick question maybe I can ask you before, as I'm switching over to Dan. Someone wrote, is this surprisingly weak response due to the overwhelming amount of heat in the ocean in areas other than the Niño 3.4?
Yeah, I think that's really a tremendous question. And of course, these are just the predictions, right? And we're actually going to have to wait to see how this plays out. And perhaps next month we'll see a shift in what's happening with respect to the forecast. But certainly, you know, we have an attribution activity that's done with our colleagues at the Physical Sciences Lab, where Andy Hull works, and he's part of that activity as well, other folks from NCEI. We will, let's suppose that this pans out, we certainly will be doing experiments to try to understand why the impact was not as strong as you might have expected given the sea surface temperature anomalies. But you actually have to do the calculations to figure that out, and I wouldn't want to speculate because I'd probably be wrong.
Great, thanks, Dave. Next, we're going to pass over for the Drought and Climate Update from Dan McAvoy. Dan is what's your formal title, Dan? I've got it somewhere here. As an Associate Research Professor of Climatology at the Desert Research Institute in the Western Regional Climate Center. Go ahead, Dan.
Nailed it. Thanks, Amanda. Okay, well, thank you for having me speak today, and thanks, Dave, for that first talk, and Andy to come. It should be interesting to hear what Andy's got to say. And so I'm gonna give an overview of where we currently sit in terms of our drought status and how the past few months of weather and climate have impacted the drought across the region. And interestingly, after seeing Dave's presentation, there really isn't a clear signal yet for California and Nevada what this coming wet season will do in terms of going back into or staying out of drought. So not a clear signal yet. So I'm going to jump right in, and first I'm showing the current drought status from the US Drought Monitor. These are maps produced for the country once a week that give updates on the drought intensity and where there is and isn't drought. So on the left is the map from September 19th. This was the most recent map for our region. And this is great to see this time of year. It's mostly white, a pretty uninteresting map with a few blotches of yellow, which is D0, kind of not quite drought, but abnormally dry. And then some very small patches of moderate drought in southeast Nevada and northwest California. And then the map on the right is showing how this map has changed over basically the past 3 months. And a lot of the drought that we did have last year was mostly eliminated after the wet winter, big snowpack and colder temperatures that we had over the past winter going into spring. But as we can see on the right there was some more drought amelioration that did occur, mostly in southeast California and southern Nevada over this past summer. And so there were a couple of pretty robust events over the last month that really made these changes and solidified this lack of drought across the region that I'm going to talk about today. So first we can look at kind of the larger scale picture of what happened over this past summer. These are the temperature and precipitation ranking maps based on PRISM climate data. And so on the left is the total precipitation for the summer, the June through August period. And on the right, the mean temperatures for that same period. And anything in green is in the top third of the distribution of rankings, and that's wetter than normal. And anything in brown is in the bottom third and drier than normal. And so what we see for California, Nevada for the summer is that most of the map is green, which is good to see. We had above normal precipitation for most of the region. So we did have a cool and wet June, and then kind of a typical July, but then we had a couple of events in August and early September that brought really heavy rainfall to Southern California into the Great Basin, and some areas recorded their record wettest summer going back to 1895 based on this PRISM climate data. And then the other thing on the right is that we didn't have an extremely hot summer, at least relative to what we've seen in the past decade or so. And so on the right, we see that across California and Nevada, it's kind of a mixed bag. There are some reds, but there are also are some blues indicating that some areas saw below normal temperatures over the summer. Some areas were near normal, but the one thing that stands out is there was really no extreme heat, except for maybe the far northwest corner of California in a very small area there. And so I want to talk about a couple of events that were really driving these climate anomalies and the drought map that we saw. And of course, the first one that occurred was Hurricane Hilary and the remnants that got drawn into California and Nevada. This actually remained a tropical storm briefly as it moved into Southern California and then transitioned to an extratropical cyclone and drew an awful lot of moisture for August into our region. And so the map on the left are PRISM estimated total precipitation for that August 19th to 21st period. Anything in that darkest shading of blue is greater than 4.5 inches of precipitation. And so there's a bunch of areas around the Los Angeles area, the southern Sierra Nevada, into the mountains, the transverse ranges, and then some of the smaller mountain ranges in Nevada that saw very heavy rain. The LA area overall got hit the hardest with about 2 to 4 inches of rainfall, and actually much greater than that, much greater amounts than that in the transverse ranges in the mountains outside of LA. And then also an area that maybe didn't get as much attention in the media was the Spring Mountains just outside of Las Vegas. This area received 5 to 10 inches of rainfall just from this event alone, and all these areas that had heavy rainfall had flooding and a lot of impacts there, but also this was ameliorating the drought conditions. And I want to dig in a little deeper into the Spring Mountains rainfall. And so again, the map on the right is showing kind of the reference area here. We see the Las Vegas area, and then just to the northwest is the Spring Mountains. And those circles are a number of snowtail sites there that record rainfall. And so I've highlighted one, which is the Bristlecone Trail snowtail, and I forgot to put the elevation, but I think this is somewhere just over 8,000 feet in elevation. And what we see is that the Hurricane Hilary remnants, and even just prior to that, there was moisture in the area, and over that 5-day period, August 17th, 6-day period to the 23rd, This station received 13.8 inches of rainfall. It got above its record rainfall in the period of record, which for this site goes back to 2009. And you'll see that light green line is the median for the water year. And so they average a little less than 20 inches for the whole water year. And so they got about 3/4 of that in about 6 days. And so this was a really significant event. Interestingly, the Las Vegas metro area got about less than an inch of rain for most places. And so the orographics of the Spring Mountains really played a huge role in those excessive rain amounts. And so on to the second event that really kind of solidified erasing the drought was the Labor Day weekend storm. And this was a much different storm than the Hillary event. This came down out of the north. It brought colder temperatures. It was a slow-moving cutoff low pressure system that lasted several days. And so the map on the left is showing the PRISM estimated precipitation totals for August 31st through September 4th. And the totals were not nearly as extreme as the Hillary event, but still there were a lot of, well, first of all, there was a large area that got widespread wetting rains of over 1/2 inch. And locally, there were 2 to 3 inches of rain for some places or even more. I was actually camping that weekend near Kirkwood, California, which is near just south of Lake Tahoe. And that area got 2 to 3 inches of rain. And I can attest it was quite cold and wet that weekend. And then it was also a cold system. So on the right is the temperature anomaly for the same period. So over that 5-day period, some places saw average temperatures 8 to 10 degrees below average. And so this event combined with the Hillary event really did a whole lot to increase the soil moisture. The air temperatures were cool, but the land surface temperature also stayed cool. And so this has really done a lot to decrease the fire danger for the area, which I'll talk about in a little bit as this is getting into what is peak fire season for a lot of areas in the region before the seasonal rains can begin around this time. And so getting back to soil moisture, we had a lot of moisture in the soil to begin with, thanks to the wet winter and the carryover of the soil moisture throughout the summer. And so this map is showing the soil moisture anomaly from September 21st from the crop CASMA estimates at 9 kilometer spatial resolution. And those darker bluish colors are showing much wetter than average soils. And so this is kind of just to show that spatial pattern of above normal soil moisture across our region, with the exception of parts of the Central Valley and Northwest California. And I really wanted to show the impact of those events had, individual events had on the soil moisture. And so this is showing the soil moisture trace throughout the water year since October 1st. Over the Central Nevada Desert Basins region, which is highlighted on the map there on the right. It's a large area, but it does include the Spring Mountains in there that I showed earlier. And what we saw is that the black line is what we saw this year. The lighter green trace is the median, and then there's the max and min. And so we see the seasonal cycle with the soil moisture increasing in the spring and early summer and then decreasing. And we saw that cycle, but it was much higher than normal going into the summer and remained that way throughout most of the summer, again, due to the wet winter and cooler temperatures. But we did see some drying happening in July and early August prior to the Hillary event. And then we see this very large spike in moisture that coincided with the Hillary event, much higher than anything that's been seen in the record for this time of year. And then we saw some drying again and a second wetting period. So brought the soils to these record levels. These sites have data going back to 2011, so not an incredibly long record, but still just a very anomalously moist environment right now. And this is the exact same thing, but now I'm showing the Carson River Basin. Nearly all of these sites are in the Sierra Nevada or in the foothills just south of the Lake Tahoe Basin area. And so a similar pattern where we saw these soil moisture records go to record values in late August and early September, thanks to those two events. So something that's related, and there are feedbacks that drive this with everything I've been talking about, is the evaporative demand, or the thirst of the atmosphere. And this is showing the 3-month evaporative demand drought index, or the EDI, that was ending on September 19th. And so we see a lot of blues and whites in our area again. So this is much below normal evaporative demand. So the atmosphere has been less thirsty. This is related to lower temperatures, higher humidities, and more cloud cover. And again, this is also correlated with lower fire danger. So it's been, the weather and climate have been in our favor for a quiet fire season. So it's not incredibly unexpected that that's what we are seeing this year for the most part, except for some areas in Northwest California. And so this is a map showing the active large wildfires. This was from September 22nd, and a large wildfire here is defined as greater than 1,000 acres in size. And so the map is almost entirely blank except for that Northwest California area, which is good to see. It's been a very quiet season for the most part. Much of that related to the climate and weather that I just went through. But there is a big complex in Northwest California right now still burning, the Smith River complex, over 94,000 acres. But it is getting contained currently at 85% containment, and perhaps some rain in the next week will help to get that contained even more. So moving on to the water supply is also in good shape. This is also going into the reasoning why that drought map is mostly white right now. And so I couldn't find a good graphic to show this, but I wanted to highlight some of the reservoirs, the reservoir status throughout the state of Nevada first, and then California. And again, the big winter, the deep snowpack, above normal runoff throughout the spring and summer really filled up those reservoirs across the region, and pretty much everywhere is in good shape. I've highlighted in red the major river basins that are being shown here, the numbers, and then on the right is the percent of average for those full basins. So Tahoe Basin is at 226% of average, Truckee 129% of average, Carson River 213, the Walker River at 197, the Lower Humboldt at 225, and the only one that stands out as some concern right now is Lake Mead in the southern Nevada basins there. So Lake Mead is on the Colorado River system, and for the most part separated from the weather and climate that I've been talking about throughout this talk so far. And despite the big winter and good runoff and good inflows into Powell and Mead, it was at such historically low levels before that just a single winter like we had last year is not even going to come close to refilling a reservoir the size of Lake Mead. So it's currently at 63% of average and 54% of capacity. And so this is higher than it was last year, and I believe higher than it was 2 years ago. But it's still below that tier 1 water shortage threshold. It did raise above the tier 2 threshold, which is good, but there still is a water shortage in Lake Mead and in the Colorado River system. And so we're going to need an extended period, I'm talking years to decades, of really wet conditions to see Lake Mead come back to it near its full capacity. And shifting westward to California, water supply status, very similar conditions in terms of the fact that nearly all the reservoirs are in good shape, again, related to the winter, big snowpack and runoff from last year, and modest temperatures throughout the summer. So again, all the major reservoirs are really in pretty good shape here. The only one that stands out as maybe slightly concerning going into the winter is Trinity in Northwest California. That was again an area that was drier and hotter this summer. And Trinity is currently at 85% of average and 53% of capacity. So not terribly bad, but something to keep an eye on going into the winter season. And so the last thing I wanted to talk about, getting back into ENSO before we shift to Andy's talk, a tool to look at some of the relationships between ENSO state and total precipitation. This is on the Western Regional Climate Center website. The link is down there at the bottom. So this is a page that has been around for a while, but there's recently been a few updates. And so what we have available here are scatter plot graphics, like the one showed on the bottom right, that compare the ENSO state to total precipitation. And so one restriction to this tool is there is right now only one option for both precipitation and ENSO state. And so this looks at the June through November averaged ENSO state using either the Southern Oscillation Index or the Niño 3.4 anomaly. That was a new addition we added. And it compares it against the October through March precipitation totals, basically looking at the response of the cool season precipitation totals to the ENSO events. And this was all based on work that Kelly Redmond and others did back in the early 90s to come up with the strongest relationships between ENSO, or what they can find being the strongest relationships between the Southern Oscillation Index and seasonal precipitation. And they were really focused in the Western United States. And what they found was that June through November lag was really one of the better indicators of the cool season precipitation. We do have potential in the future to add more averaging periods and lags. For example, we could look at autumn ENSO patterns versus winter precipitation. So there is potential to add things like that. And so the old pages had just the Southern Oscillation Index and a handful of NCEI climate divisions to look at. So what we've added now is, in addition to the Southern Oscillation Index, the Niño 3.4 anomaly, and also the ability to look at any NCEI climate division across the United States. And one thing we don't have that will be coming soon is a link to a map, which we should have added already, to show where those climate divisions are. And so I just want to show a few examples here. And so this one is for the Nevada Northwestern Climate Division. So this is where I'm at in Reno, and it covers a large area in Northwest Nevada. And so on the left, we have the scatter plot using the Niño 3.4 anomaly, and on the right, using the Southern Oscillation Index. And so on the horizontal axis is the ENSO state, and then on the vertical axis is the total precipitation. And this is for all water years going back to 1934 through this past 2023 year. And so at this particular location, there's very little relationship between ENSO in summer and autumn, and then the October through March precipitation. And so this lends to some of the equal chances that we saw in Dave's presentation for our area, but doesn't explain everything. Of course, there's a lot more going on, and there are different lags and averaging periods to consider. And you'll see that the SOI and Niño 3.4 indices show similar patterns, even though the intensities are reversed due to the sign that is used for El Niño and La Niña. And just one last example showing a bit of a stronger relationship in the southern coast drainage, which is basically Southern California coastal area, where we see that there is a bit stronger relationship showing that mostly that the La Niña events have been drier than average for the most part, although there are a few outliers there. And some of the strongest events, precipitation totals, have come from strong El Niño events, but again, there's a lot of variability there. The R squared is 0.11 for Niño 3.4 and 0.15 for the Southern Oscillation Index. So these can be used to get a sense if El Niño does tilt the odds towards wetter or drier for your area. And I think that might be a good way to segue into Andy's talk. And so I will stop there and take questions at the end if there's time. So thank you.
Great, thanks, Dan. Let me just change speakers here. Next to present is going to be Andrew Hoyle, who is a research meteorologist with NOAA's Physical Science Laboratory. And take it away, Andy.
Thank you, Amanda. Thanks for having me. Thanks, Dan, for having me as well. And yeah, today I'm going to present on the relevance of El Nino intensity for Western U.S. precipitation. And this is a follow-up on a paper we did a number of years ago on the same topic, but for California, Nevada. So moving on to the next slide. These are the three main points that I'd like to make. The first is that precipitation differs between El Nino events. And I think we learned that the hard way in 1516 during the last strong El Nino event. And I'll highlight that and the overall changes in the odds and the frequency of above average precipitation during El Nino events in the observed record. Because observations provide only a fairly small sample size, what I'll also do here is to try to constrain the odds of how strong El Nino events are related to precipitation in model simulations. And what we found there is that stronger El Nino events are related to more precipitation. And then finally, what the sort of the conundrum that was highlighted before is above average precipitation is related to strong El Nino events. We're not seeing those kinds of odds in precipitation forecasts from dynamical models. And I'll contrast that perspective from the dynamical models that Dave had alluded to before with what we're seeing here in the observed history. So moving on to the next slide. Next slide is just to indicate that we're moving on to the differences in precipitation between El Nino events. So next slide here. So 82, 83, and 97, 98, they shaped our expectations for strong El Nino events, and perhaps unfairly so. So in this map, and the sequence of maps that I'll show in the following slides, are the precipitation percentile rank compared to the long historical record, 1896 to 2022, in NOAA NCEI NCLIM grid. And what we saw in 82, 83 was exceptional precipitation across the Western United States. Greater than 95 in the 95th percentile, some areas even reaching their maximum value in areas like California, Nevada, and even other areas in the Western United States too. The only area where we did see low precipitation was in those higher elevations of Montana, even down into Wyoming, and perhaps even into Colorado as well. Now, the next slide shows 97, 98, where 97, 98 produced some of the same features as 82, 83. Perhaps not as intense across the Western US, but pretty similar in the sense that we saw very far above average precipitation, and historically so over California, Nevada, in the southwestern United States, alongside that familiar feature of below average precipitation in northwestern Montana. Now, also interestingly, it is in Washington and Oregon, where we tend to see below average precipitation in the aggregate of El Nino events, but during strong El Nino events like 82, 83, 97, 98, not so much. And then the next slide, which shows us 2015, 2016, which gave us a dose of reality and altered our expectations for strong El Nino events. So if you were to look here at the panel on the right and see 15, 16 precipitation percentile ranks, you'd probably be hard-pressed to say that's an El Nino year. And the reason for that is quite a bit above average precipitation, historically so, over Washington and Oregon. Historical precipitation over areas of Nevada. But the further southwest you go, like Southern California, Arizona, below average precipitation. This was a conundrum and is often researched and referenced by researchers like myself within the forecasting community as to why this happened. And there's a couple of different reasons. We can talk about that in the question and answer session, but mostly boils down to two main culprits. One, differences in the behavior of the El Nino event itself, and also behaviors elsewhere in the climate system that play a role. The next slide right here is an aggregate picture of what conditions we tend to see during strong El Nino events in observed estimates and observed conditions. So what this includes here is 1957, 1958, 72, 73, 82, 83, 91, 92, 97, 98, 09, 10, and 2015, 16. And what it does is it calculates the frequency of above and below average precipitation during these El Nino events. And what we find here in the aggregate of the historical record that we have for strong El Nino events is a very high likelihood of above average precipitation over the southwestern United States, with particular emphasis on California and Nevada. You go further to the north, you see an elevated likelihood of below average precipitation. Those areas like in Montana, Idaho, and even in the Pacific Northwest as well. So this right here, despite the fact that it's a small sample size of El Nino events, is really the baseline from which we work toward when it comes to strong El Ninos and their effects on Western US precipitation historically. So moving on here to the next slide, what tends to happen here is that in observations, we have very small sample size. Yeah, they're good guideposts, but we tend to use model simulations to be able to bolster our confidence in what patterns that we see, their likelihoods, their frequencies, and so on. So moving on to the next slide, this is what the sequence of next slides are going to be. They're going to be based on analyses from the Community Earth System Model version 2. And what we're going to show here are certain characteristics of precipitation related to strong and moderate El Nino events. On the left is strong, on the right is moderate, and this is relevant to October to April. And what we're doing here is showing the frequency of above average and below average precipitation. Above average being the 66th percentile and above, which is the classical definition of above average, and below average being the lower tercile, lower than the 33rd percentile. Just comparing these two maps right here, you can clearly see that stronger El Nino events are related to higher frequencies of above average precipitation. And the frequencies are quite strong, actually. We're talking about 60, 70, 80% likelihood of above average precipitation in the Southwest, and especially over California and Nevada. Looking at moderate El Nino events, we do see a tilt in the likelihood to above average precipitation, but looking at a tilt in the odds of about 40, 50, 60%. So nothing to sneeze at, but strong El Nino events definitely dwarf moderate El Nino events regarding the likelihood of above average precipitation. So moving on to the next slide here, what the next slide shows is the likelihood of extreme precipitation. Extreme precipitation here is taken as the top decile or greater than 90th percentile of historical precipitation. So basically quantifying the likelihood of extreme precipitation over the Western United States related to strong and moderate El Nino events. And to nobody's surprise right here, we have an elevated likelihood of extreme precipitation during strong El Nino events. So over California, Nevada, we're looking at somewhere along the lines of 30, 40, 50, even 60% chance of precipitation in the upper 10% of the historical distribution. That's basically a 5-fold increase in extreme precipitation likelihoods there. So a strong El Nino event really tilts those odds to above average precipitation and extreme precipitation. Moderate El Nino events do the same, however, not with the same chances, not with the same likelihood. You can see here that there's about a 2-fold increase in extreme precipitation, perhaps a 3-fold increase over California, Nevada. Now moving on here to the next slide, what I'm doing here is to just focus on California, Nevada, and the plot shows the precipitation exceedance likelihood, where precipitation is measured as a precipitation percent of average on the horizontal axis, and the likelihood of exceeding that value is on the vertical axis. And again, we're showing strong El Ninos on the left and moderate El Ninos on the right. And what's apparent here is that we are getting some pretty impressive odds in terms of precipitation percent of average in strong and moderate El Nino. So if I were to show just the entire history of precipitation within the Community Earth System model, what you'd see here is a pretty big shift to the right, meaning a shift to the right indicates a higher likelihood of above average precipitation. Just comparing these two right here, you can even see that strong El Nino events give you that shift to higher likelihoods of above average precipitation compared to those in moderate El Ninos. So one thing that I'd like to highlight here is that if you were to look at 100% of average, so basically average precipitation, a strong El Nino event gives you essentially an 80% chance of that happening. And then if you were to go out to 125% of average, you have a 50% chance of that happening. So what we're talking about here during strong El Nino events is really that elevated likelihood of high precipitation. And if someone wants to have some grins and some chuckles, you can look out there to about 180 or 200% of average, where you get a 3 or 4% chance of that happening. Moderate El Nino events also increase the likelihood of above average precipitation, certainly not with the same sort of frequency and likelihoods that you see during strong El Ninos, but a moderate El Nino definitely shifts those odds to above average precipitation as well. So moving on here to the next slide, what I'm going to highlight here is a little bit of what Dave was talking about before, that precipitation in the forecast models that we use, and there are many in our community, they are not indicating as high of a likelihood of above average precipitation as we would anticipate see during a strong El Nino event. So moving on here to the next slide. This is a forecast ensemble that is put together by the World Meteorological Organization. It brings together models from many different sources here, and they're listed actually by the city that that the modeling center is located in. So there are 5 models that go into this ensemble, and the reason why I chose this is because we can look at precipitation from October 6 months hence, so October to March, and the shift in the likelihood of precipitation. If you look at the southwestern United States, there's about a 40% chance of above average precipitation. There is that shift in the likelihood to above average precipitation, but if you compare these maps right here in the forecast ensembles to those in the historical analyses and also the climate models that I showed, they really pale in comparison. And this right here is a little bit of, we don't want to go on a limb right here and begin to speculate too hard on what could be causing this, but it's certainly a little bit of a surprise that we're not seeing the shift in the odds to above average precipitation over the Southwest and even the entire United States, the southern tier of the United States in general, related to this forecast strong El Nino event. So with that, I will wrap up my presentation, and thanks to the conveners for having me.
Thanks, Andy. Let me just change over before we go to a few questions that have come in, but feel free for others to put some questions in the questions box. Thanks to everyone for joining us, and thanks to all our great speakers. Before I take on questions, I put a reminder link in the chat that this is being recorded, and you can have a summary later this week for sharing on drought.gov and our YouTube channel at the link. With that, let me pop open the questions box. One of the ones I think that came in while Dave was presenting, but Dan, I think you could answer, were what were the precipitation predictions like this time last year? I'm guessing their questions coming from it was very wet last year, so they sort of wanted to compare the 2 years.
Yes, and you know, and I don't know if Andy remembers exactly what they were. I feel like the forecast models were, since we were still in a La Niña pattern, indicating the odds were slightly greater for below normal precipitation in the Southwest, although not huge probabilities, and shifted to slightly higher odds of above normal for the Pacific Northwest. And that didn't pan out that well, if I remember correctly, at least with the forecast. Is that what you're remembering, Andy?
Yeah, I remember that all too well, and we're actually researching that last winter in comparison to prior ones. So the last 3 winters, what we saw was a below average precip forecast, about a 40 to 50% probability over the Southwest, above average precipitation forecast over the Northwest related to La Niña. And last winter, that forecast did not pan out. In fact, it was very wet over the Southwest. And yeah, in prior winters, they panned out pretty well. So it's always interesting to see how you have a most likely outcome on your forecast and see how that actually compares to what happens.
Yeah, and I've been getting a lot of questions as to why that happened. And I keep saying, well, talk to Andy Hoyle. He's probably working on it right now. So we're expecting some results soon, Andy.
Yeah, actually the Madden-Julian oscillation was very active during the 2 periods of last winter where we saw a lot of precipitation in California and Nevada. So we're researching this right now, but that's our null hypothesis where the MJO was really impactful for last winter.
Great. Thanks, guys. This one's another one. This one's for Dan. I think it came when you were showing the fire, where the current fire situation was or had been this season. And they're asking, are the Northwest California fires associated with the fact that the temperatures were higher and precipitation was lower than normal there?
Yes, I think that was one of the big drivers. That gradient across California from hot and dry to cooler and wetter, there was a really strong gradient across northwest, north central California where things got drier, stayed drier and warmer in that northwest corner, associated, I think, mostly with the kind of persistent ridging in the Pacific Northwest and in the Northeast Pacific. That also led to the increase in drought across Oregon and Washington. So that was kind of the southern edge of that pattern. And that was certainly one of the big players in increasing the fire danger there throughout the summer. And I don't know the particular causes of what those fires were.
And then the last question I see so far, I think it was when you were showing the, oh, there's one more after that. The El Niño Southern Oscillation scatter plots. They asked, have you looked at the relationship with El Niño Longitude Index, ELI?
No, we have not. But that is something to consider. We are taking feedback, and that is very welcome. And I will say we are considering making this more of an interactive tool down the road where you can actually hover over the dots so you can see what years they are. But so far, we've just incorporated the Niño 3.4 index, as that is one of the more common ones. But I know there are a number of other indices out there to consider. So thank you for the feedback.
Okay, there's two more that just came in here at the end. I'm not sure which one this one was for, but both of you, let me know who should answer. To what extent does ENSO flavor, e.g. CP versus EP, matter?
I'll let Andy take that one.
Yeah, so EP, CP, they do matter. Those flavors have distinct teleconnections meaning the connection between what's going on in the El Niño regions and El Niño behavior and North America. And this gets back to 1516, where a lot of folks are arguing in literature that 1516's El Niño was more of a CP variety, more of a Central Pacific variety, and therefore did not have the same impact on, say, California, Nevada, the Western US as 82, 83, and 97, 98. So they do play a role. There's been confirmation in the literature on that.
Okay, thanks, Andy. And the last one, so this one starts with a question, then has some comments in here. I think it's your presentation, Andy. There it says there are only 4 main strong El Niño events. So the last slide seemed based solely on 82, 83, 97, 98, correct. Last year, 2002 had a very low chance of 100% of average and below 10% of 150% in California. Adding that to 2015-16 results leaves little confidence in messaging, even though ENSO strength is confident, and that confuses the precip forecast message. In parentheses, very low confidence. The biggest snowfalls, for example, in Mammoth are now La Niña, 2011, 2017, and 2023. So it was a long sort of comment question, I think, about your presentation, Andy. I don't know if there's anything you'd like to say.
All good points. Trying to filter out a question in there, and if the
yeah, it's at the beginning. You said there are only 4 main strong El Niño events. So the last slide seemed based solely on 82, 83, and 97, 98. Correct?
It depends on how you define a strong El Niño event. So, for example, Climate Prediction Center and their probabilistic experimental outlooks are defining a strong El Niño event to have a Niño 3.4 great index of greater than 1.5 degrees Celsius. That lowers the bar quite a bit, increases the sample size. So on my slide 7, what I did was to include those years that qualified with that 1.5 degrees C Niño 3.4 threshold. So that increases the sample size to 7. So 82, 83, 97, 98, 15, 16, in addition to others within the record since 1950.
Okay, great. With that, those are all the questions that I see. So I just want to thank everyone for joining us and for your questions. And if you have any remaining questions, feel free to reach out to my email. I believe it's on the slides here, so I can connect you with any speakers that you need. And if you want to become more involved with the California Nevada Drought Early Warning System, including this webinar series, please also reach out to me and I'll be happy to connect you to that. So thank you again, Andy and Dan, for your great presentations and everyone who attended, and have a great week.
Thanks, Amanda.
Thanks.